In this lecture we are going to discuss torsion design minimum and maximum requirements. So if the ultimate torsion on a cross-section exceeds the threshold torsion value that we have already discussed in previous lectures, then you have to meet the following requirements according to ACI 318. The first one has to do with minimum transverse reinforcement. You can find this in ACI 11.5.5, and it states that if you add the shear reinforcement and 2 times the torsion reinforcement per leg, as a minimum, it should be equal to 0.75 square root of f prime c times the width of the cross section times the spacing divided by the yield stress of the reinforcement. So that's this formula right here. So it basically says this is right here, this is the shear reinforcement that we've already presented how that's computed, and this here is the torsion reinforcement per leg. Usually our transverse reinforcement is a stirrup like this, and so the reason that there is a factor of 2 is because torsional gives you the value that you need for transverse reinforcement for one leg. You need to multiply that by 2 to get the total, and then the shear reinforcement is already automatically the total. So that's why that formula looks like that. In any case, that value has to be, as a minimum, 0.75 square root of prime c b times s divided by fyt. But it cannot be, under any circumstance, less than 50 times the base of the cross section times the spacing divided by fy. And that's that formula right here. So we have 2 requirements. Whichever one governs is the one that you should use. So this is the absolute minimum. So these are requirements for transverse reinforcement. For longitudinal reinforcement, and that is the reinforcement that is going to be used distributed around the perimeter of the cross section in order to resist torsion. If your ultimate torsion is greater than the threshold torsion, then as a minimum you have to use this expression right here. So that's 5 times square root of f prime c times ACP, which we have already discussed, divided by fy minus AT divided by s times pH times fyt divided by fy. As we remember, pH is the perimeter of centerline outermost transverse reinforcement. So it's basically this perimeter right here, right? And if you remember, ACP is the area enclosed by the outside perimeter of the cross section. So that is that perimeter out here on the cross section. So ACP, area enclosed by the perimeter of the cross section, pH, perimeter of the transverse reinforcement. AT is the area of one leg of transverse reinforcement, and S is the spacing. Moreover, the spacing of the transverse reinforcement in a beam reinforced for torsion. So now if I draw the beam sideways, let's say this is the beam sideways, these are supports, this is my longitudinal reinforcement. Again, I'm drawing it sideways now, and I'm drawing the transverse reinforcement right here. The spacing of that reinforcement has to be less than this value right here, the minimum of pH over 8, right? pH being the perimeter of the center line of the transverse reinforcement, or 12 inches. In terms of dimensions, the dimension of a cross-section that is resisting combined effects from shear and torsion has to satisfy this requirement presented here. And this requirement basically ensures that the size of the cross-section is adequate to resist the combined effects of shear and torsion. That requirement can be found on ACI 11.5.3. So you can see here that you have the ultimate shear computed from the load combinations, the ultimate torsion. You have some properties of the cross section, and on the other side you have phi, which is the same for both, 0.75, and then VC divided by BD and 8 square root of F prime C. As you may remember, this VC is computed depending on whether the section is subjected to tension, compression, or moments combined with shear, and in most cases this is equal to 2 square root of F prime C BWD. So when you plug this in, this parentheses will most likely be around 10 square root of F prime C. So this basically establishes a limit on how small a cross-section can be in order to resist the combined effects of shear and torsion. In this formula, just as a reminder, AOH is the area enclosed by the center line of the transverse reinforcement, and pH, again, is the perimeter of the center line of the outermost transverse reinforcement. A couple of details related to the transverse reinforcement and the longitudinal reinforcement. In order for a transverse reinforcement to be effective for torsion, it has to be closed as what we call a seismic hook. So that hook, when you make the stirrup, it has to lock in at the ends with two hooks that are at least 135 degrees. So I'm showing here the hook on the coming in on the left. You would have to do the same for the one coming up, but you have to hook it 135 degrees so that it actually locks in. This means that you can't have transverse reinforcement for torsion that looks like that. That is okay for shear, but it is not okay for torsion. This kind of transverse reinforcement is not acceptable for torsion. In addition, the longitudinal reinforcement has to be distributed throughout the perimeter of the cross section. So let's suppose that this red reinforcement here is used for resisting bending moments. Whatever additional longitudinal reinforcement you have for torsion, which would be this usually smaller diameter bars, these bars have to be distributed across the perimeter. So what it means is it is not acceptable for torsion reinforcement to have something where you just put a couple of bars, let's say one here and one here, for torsion reinforcement. That kind of torsion reinforcement is not acceptable. It has to be distributed along the perimeter. So like this. That kind of torsion reinforcement is acceptable.